Okay, welcome back. We got to do two more problems, 64 and 67. Problem 64 wants us to use figure 2315, which I already drew, and 22 ohm lamp and a 4.5 ohm lamp, that's why they're looking like light bulbs instead of resistors, are connected in series and placed across a potential difference of 45 volts. So this guy here is 45 volts. What is the equivalent resistance of the circuit? Okay, equivalent resistance of a series circuit is add up the resistances, R1 plus R2. So 22 plus 4.5, that's 26.5 ohms. Then for part B, what is the current in the circuit? Once you know the full equivalent resistance and you know the voltage in the battery, you can find the current. So V equals IR, where R is the equivalent, I is the current going through the battery, and V is the voltage of the battery. We would like to find the current, so I is equal to V divided by R. So that is 45 volts divided by 26.5 ohms. So the current is equal to 1.7 amps for part B. For part C, what is the voltage drop across each lamp? We know the current. If we know the current and we know the resistance of each lamp, we can figure out how much voltage they each use. So the voltage used by the 22 ohm resistor is equal to the current going through the 22 ohm resistor multiplied by the 22 ohm resistor's value. And so that is 1.7 amps being multiplied by 22 ohms. So the voltage consumption of the first light bulb is 1.7 times 22, 37.4 volts. That's the first part. The voltage going through the 4.5 ohm resistor is equal to the same amount of current, 1.7 amps. Remember, series circuit, all the same current, and 4.5 ohms. And so 1.7 multiplied by 4.5 gives us 7.65 volts. And notice, please, if we add up 37.4 and we add 7.65, we get 45.05, which should be rounded off to 45, which is the voltage of the battery. Then for part D, they would like to know what is the power dissipated in each lamp. So the power dissipated by the 22 ohm lamp is equal to the current going through the 22 ohm lamp multiplied by the voltage consumed by the 22 ohm lamp, and we know both of those values. So 1.7 amps being multiplied by 37.4 volts is equal to 37.4 times 1.7 is 63.6 watts. Not being very good with significant digits, but that's okay. The power going through the 4.5 ohm resistor is that same current, 1.7 amps, multiplied by its voltage consumption, which was 7.65 volts. And therefore, we end up with 1.7 times 7.65, 13.0 watts. And the power that is being given off by the battery is equal to the summation of this one plus this one, or 76.6 watts. They didn't ask us for that, but it's an easy thing to find. Question number 67, if I can wake up my phone again, somewhere in here. Question 67, figure 2318, which is the one below us. The battery develops 110 volts. Okay, so now we have a series circuit, and we have, let's move this guy up here, get a good picture of this guy. They just said 110 volts. 110 volts. Sounds like it might even be plugged into a wall outlet, and this might be a this might just be a AC circuit, which for our purposes behaves the same way as DC. That's a simplification, but it works for first order problems. Okay, so this guy here was 20 ohms, this guy here is 50 ohms, this guy here is 10 ohms, and we got 110 volts. Now, here's the beautiful thing about this. Being in parallel, they all can make a path straight back to the battery or wall socket, whatever thing that is, whatever voltage source that is. And so they all get the whole voltage. So they want to know which resistor is the hottest. Ooh, okay. Hottest is power. Okay, power is proportional to hotness or rate at which heat is released. So the one with the greatest power consumption will be the hottest. That would be the answer to A. And the one with the smallest power consumption will be the coldest, which is the answer to B. All right, so I'm going to, at the bottom of each one, I'm going to figure out what their powers are. So I'm going to call this branch 2, this branch 3, this branch 4, because that's the numbers on the ammeters. So the power consumed through branch 2. Now, again, remember we have several things. We have we have power is current times voltage. We don't know the current yet, so let's ignore that. We also have power is, where'd it go? Power is current squared times resistance. Again, we don't know the current, so we don't want to use that one. And the last one was power was voltage squared divided by resistance. This one we can totally do. So they each get 110 volts, and that's got to get squared, and they're all going to have the same value of that. And then in the bottom, we're going to put their respective resistances. So if I put the 20 ohms in here, because I would like a real number for this one, then I've got 110 times 110 divided by 20, and that's 605 watts. Now, I'm going to do this conceptually here because we don't really need to calculate every one. If I have a smaller number here, that's going to give me a larger power. So that means that the hottest one, the one that has the most power, is over here. That is the winner for A. So A is the 10 ohm branch, or the ammeter 4 branch. If I have the largest number down here possible, I'm going to get the smallest value of power. So that makes the second branch, or the one going through ammeter 3, the coolest one. So those are the answers to A and B. Then they would like to know what are the values through the different ammeters. Now for C, they would like to know A1. For D, they would like to know A2, E is A3, F is A4. I would rather not start with A1 because we've got current here, plus current here, plus current here, giving us current A1. So C is V equals IR, so I is equal to V divided by R. So in this case, we've got 110 volts divided by 20 ohms, and so we've got 11 divided by 2, which is 5.5, so that's current 2 is equal to 5.5 amps. For D, current 3 is equal to voltage 3 divided by resistor value 3, which is 110 volts divided by 50 ohms. So 110 divided by 50, 2.2. 2.2 amps. And then for E, they would like to know, I think I got my letters wrong. And my phone turns off again. Yeah, I messed these up. C was the one I wanted to skip. So this was actually D, this one's actually E, this one's actually F. So current 4 is equal to voltage across 4, which is 110 volts again, divided by resistance 4, which is 10 ohms. That's easy enough. That's 11 amps. And current 1 is equal to current 2 plus current 3 plus current 4. So this is the answer to C, which is the summation of these guys. So 11 plus 2.2, that's 13.2, plus 5.5, so that's 18.7. 18.7 amps, and we are done. I hope that was easy enough to follow.